Glenn Tepfer, and I want to thank you for joining me today for the first PDH Hour webinar with Glenn. For those of you that don't know me, I've been doing construction quality assurance for over 30 years, ever since 1990, and I often present topics that I see from a field perspective at geosynthetics conferences and other conferences around the world. So there's been several developments that led me to believing that I needed to do a webinar to help try and educate people. We're doing a big push for education right now in the industry. I'd like to welcome all of you, especially those that are coming from beyond the United States, internationally, from like Chile, Argentina, New Zealand, Brazil, Mexico, Switzerland, Canada. I thank you all for joining. Anyone who stays here through the hour that's registered will get their PDH mailed early next week. And I'd like to use the question and answer feature at the very end. There will be questions, and I'll try to address as many as I can before we close. I'd like to take those in written form. I think you can type them at any time, and then when I get to the end, I'll go through any of the questions and see if we can get some answers to you. Anyway, we'll get started here. Manufacturer's guidance, the missing link to quality geomembrane installations. What I'm going to do is in the outline, I'm going to look at different documents that I examined, give you a brief summary of the findings, reveal to you what I believe the missing link is, the importance of this information, where you can find it when the manufacturers don't provide it, why I believe the manufacturers should be responsible for this information, what we can all do in the meantime, and then I'll give you a brief overview of my next webinar, and then we'll get to the questions and answers. So the content that I looked at and our team looked at provided by the manufacturers, we looked at different drop-in specifications, different installation guidelines, installation specifications for construction quality control, construction quality assurance, and we looked at installation quality assurance manuals. And a brief summary of what we were finding. Really, a lot of inconsistencies just in the documents for manufacturers contained here in the United States, such as AGRU, SCAPS, Solmax, and then we looked at some international ones as well, and they all varied. The content all varied. Some, the common elements, material delivery, unloading, handling, things that are going to get you through the whole installation, basically from receiving your material all the way through final walkthrough and acceptance. Different non-destructive seam test methods. Often the ASTMs were referenced. Your documentation. So one thing we found that was consistent is that what I call the missing link was missing from every document we looked at. And that missing link is specific guidance on the welding of geomembrane, specifically thermal welding. When you look at thermal welding, as this diagram was provided to me several years ago by Eddie Weiser from Leicester, he calls it a magic triangle, but there's three critical components needed to produce a weld and to produce a quality weld. It's energy or heat, speed, and pressure. And those three are going to be combined. And you can see on his illustration that he provided, HDP and LLDP fall in one region of that triangle, the magic triangle, and then PVC falls in another. And each material is going to have its own sweet spot. But I think it goes probably beyond each material, as we'll get into here in the next 45 minutes or so. Quality welds. I think everybody that's attending this webinar would agree we need quality welds. Otherwise, your containment system's going to fail, and we don't want it to fail. The whole purpose is to contain, so welds failing are going to result in leaks, which are not containment. Quality welds should not be optional. They should be mandated. And I was just watching a recent interview by Dr. Kerry Rowe, and he did a nice job detailing that, there's a need to ensure good quality welds. But that led me to ask the question, how do we define a quality weld? Here in the United States, a quality weld really seems to be defined by passing a non-destructive test in the field and then meeting shear and peel requirements, your strength, peel incursion requirements, elongation at break and such. So how many of you agree with this? I can't physically see your hands here, but I know it's a mix. Some people agree and some people don't. But I believe it needs to go beyond peel and shear, but that's not really the focus at this point of my webinar. So we ask, why are these components so important? These parameters, your heat, speed, and pressure. Well, to provide guidance to the installers so they don't damage the geomembrane during welding. That's a top priority. And then with the onset and more usage of data recorders, there needs to be a good foundation for the data so you can make logical and accurate decisions. And so that information is critical to making those decisions. As far as guidance to the installer goes, the trend here in the United States is to overheat our seams. You can see this photo here. It's a fusion seam on a 60 mil geomembrane in a cell, and it's significantly overheated. But when I talked to the installer about that, I suggested that they replace the seam, and then he argued with me, and I suggested, well, this is the worst part. You need to at least replace this. And he said, take a destruct. It's going to pass the peel and shear test. And he's right. That's unfortunately the attitude and mindset of a lot of people in the industry is it's going to pass the peel and shear test, so therefore it's okay. And then, so my next step as a CQA technician, I go to the engineer, the certifying engineer. Well, he basically says the same thing, if it passes peel and shear, it's okay. His hands are tied because it's not in the specifications or construction documents. This is an illustrator, a sample, probably out of that same geomembrane or pretty close to it there, where it just shows, this was part of a paper I did on this, but the overheating, you can see, a severe ridge. I mean, that's indented. There's a thickness reduction there. And the same thing is happening to our extrusion welds. This was a project where they were having a hard time, the installer was having a hard time getting the extrusion welds to pass. They were having a 25% failure rate on extrusion samples when we took destructs on them. So they um, alleviated that and they got their passing rate down to like 5% or so. But they did it by overheating the geomembrane. You can see how the geomembrane is distorted and kind of sucked up into where the heat was. And that's all so it can pass a peel and shear test. There's no way this material would even peel at that point. It's getting so heated and stressed that it can't even peel. It's bound up on itself, and the material can't physically get unlodged in some of those samples. So why is overheating so prominent here in the United States? First and foremost, I do believe it's a lack of guidance from the manufacturer. I think that, fundamentally installers want to do a good job, but, it's a double-edged sword with installers. A lot of installers reward their welding technicians for not failing destructive samples. And so the technicians cheat and they overheat them because they will pass the peel and shear testing as long as they don't overheat them to the point that the shear fails. And there's a big window between the two. So the impact of overheating, there's plenty of papers out there, but ultimately what happens in overheating is it's changing the molecular structure of the geomembrane, the chemical composition. You get a loss of oxidation induction time, and that results in the increased likelihood of stress cracking along the area of the weld. It's going to be parallel to the weld, not necessarily in the weld itself. The weld in itself usually is going to pass and maintain its strength unless it's significantly compromised. But in looking at some of the papers from Dr. Rowe and Dr. Peggs, I used as a reference when putting this together, I illustrated on a sample here a fusion cross section of a fusion weld, a dual track. You can have a weld on the left and right sides here of the sample, illustrated by the green hashes, and then an air channel in the middle so you can non-destructively test it. And then the important thing to note, though, is this heat affected zone. There's an area where the heat is affecting the geomembrane outside that weld. The heat being introduced during welding is impacting the geomembrane, and it goes beyond just the weld area. And so this sample here, you can see there's some excessive squeeze out. The air channel was reduced to 5.84 millimeters, and you have significant reduction of weld thickness. Well, here in the United States, there's nothing that we can do about it. In some other countries, like Germany, they have a DVS guideline and they actually measure the air channel and the thickness of the weld, and that's part of their acceptance criteria for the welds. So now, as a foundation for data recorders, this data is important because it correlates back to the trial weld. It only correlates back to the trial weld, I should say. Sorry, my dogs keep coming in here and want to be petted while I'm doing this. So, yeah, just bear with me. Hopefully they won't start barking, but they enjoy running around our office. So, as we talked about, we do the trial welds and they may pass just like the destructs may pass, but they may have already been overheated. They'll still pass. So we're correlating data back to a trial weld that may have failed. And then without this data, how do you define what is an acceptable anomaly? I'll show you a slide in a few moments here about the anomalies for those of you that aren't familiar with the data recorders, but there has to be some sort of a baseline there that gives you a parameter to define what's acceptable and what isn't acceptable. And then, my third concern with data recorders is people are making decisions based on them without the baseline information, and I think that's a risky proposition. As a foundation for data recorders, assessing the data here, this is a graph that was presented back in 2019 by Alan Bullock, and it shows Leicester equipment, a graph of temperature, speed, and pressure during welding, and the weld started here on the left side, and then the distance was, I can't read it on the slide, but it monitored the whole distance. And so you're looking at these graphs for, the three parameters of the magic triangle: temperature, speed, and pressure. And, this graph showed here there's an anomaly, and they confirmed a leak at this location in the field. But then my immediate question that I've been trying to get answered ever since, for the last 2, 3 years, as I have time, is what about these other things? Like, here's an anomaly to the right. How do we know that wasn't unacceptable? They didn't find a leak there, but how do we know that the geomembrane wasn't compromised in some manner there? Same thing with your speed and your temperature. They're not straight lines, they fluctuate. So how do we know these fluctuations are within the approved window? And I'll get into all that in the next webinar in December, but I just wanted to touch on it a little bit. These are important as a foundation. The more we are relying on data recorders, and even without them, it's critical information. And this is just an article from Geosynthetics magazine back in October, November 2022, but there's a lot of things I disagree with in this article, and I think that it's risky. The authors are proposing that you can limit geomembrane destructive testing because you have data recorders, but if you don't know the parameters and when they fall outside what's acceptable, how can you make those decisions? Um, so really, the manufacturers, as I said, we couldn't find the information there. So if they're not providing it, where can we find this? That was my next question. So went into having myself and other members that work with me on our team trying to find, what heat, speed, and pressure should you use for different geomembranes. And we looked at some of these guidance documents here, the US EPA document from October 1992, which is really by many considered to be the Bible when it calls to quality control, quality assurance of geomembrane installations, waste containment facilities. We talked to other experts in the industry. They referred us to the IAGI website, to the guidelines for installation of HDPE, LLDP, and geomembrane installation specification. Well, that specification is dated November 1st of 2015, and it's significantly outdated as far as the content in there does not agree with other content that's currently available in other sources. But that aside, it also did not mention your heat, speed, or temperature to weld any of the materials at. So we started looking, other internet searches and reference materials. We did an AI search on the internet for fusion welding, and we found a temperature range there. We found a speed and we found a pressure. And then Leicester, there was an article by Leicester online, and the references for these are below Leicester and the DVS. We looked at the German DVS, and then we also looked at IAGI, which again did not have temperature, speed, or pressure. And the same thing for extrusion welding, only there was less information available, at least in the data that we were able to find. And we did a pretty thorough and extensive search in trying to put this presentation together. So the next place we looked, we went to the welding machine manufacturers' data. We looked at several manufacturers that are used here in the United States, and we found data for two of them. There was more specific data available based on material thickness. Here we have a table from Leicester, and they list their different wedge welding machines down in the bottom left here for HDPE. And they list different materials. Obviously, they have LL and PVC, but for the focus of this webinar, to keep it within time constraint of an hour, I really focused on HDPE because that's one of the most common materials we see used here in the United States. And then Demtech was another one where we found information available. And they also have, the same thing for LL, HD, different materials, and their welding speed and temperature. Oh, temperature and speed there. Excuse me. So I did a quick summary looking just to see what the differences were between the two manufacturers, welding machine manufacturers that we found. And in looking at the 1.5 millimeter 60 mil HDPE and 1 millimeter 40 mil LLDPE, you can see Demtech had a temperature and speed. They don't have a pressure defined on their machine. Leicester has temperature, speed, and pressure for both the materials as well. But what I thought was really interesting and kind of raised an eyebrow is that there is a difference of 60 degrees Celsius or 140 degrees Fahrenheit on the 60 mil between the recommended starting temperatures. And that just seems like a pretty significant difference to me. 140 degrees, I mean, that's quite a bit of heat. Even 68 degrees on the LL or 20 degrees Celsius. It's a big difference. So, is the difference just in the machine, the configuration, or is it, maybe there needs to be guidance from the manufacturer here? Um, and I don't have a true answer to that yet, but here is why I think the manufacturer should be responsible for the data. There's several points under this. Excuse me. Um, First of all, some of the scopes make it seem like this should be within their scope of the document. For instance, Agru's scope in the drop-in specification says it covers the technical requirements for manufacturing and installation of their HDP and LLDP products. So, to me, the heat, speed, and temperature really falls under the technical requirements. Um, and then all work is going to be performed in accordance with these procedures provided in these specifications. Excuse me. Sorry, my throat gets scratchy when I talk for a while. But all the work is supposed to be done in accordance with these documents. So, at some point, it seems like this guidance should be there. And more so, it seems like the manufacturer should provide this guidance because each manufacturer has different variances in their proprietary formulations that are secret. They're not provided, to the public. They're proprietary, and they're going to make their material react a little differently for each material, and that's probably going to impact the heat, speed, and temperature at which is needed to be welding. Each material, this table from Waste Containment Facilities Guidance for Construction Quality Assurance by Daniel and Kerner. Um, List what you can see here, typically, at least in the United States, your resin, carbon black, and additives for HDP, LL. Eddie Weiser gave more broad, what you typically see throughout the world because they sell equipment all throughout the world, but it pretty much follows the same formulation you see in the United States. And so what I did is try and illustrate this on a uh, slide here with a circle being the HDP welding um, zone within the magic triangle that was presented by Eddie Weiser. So you have your heat, speed, and pressure. Inside, you're going to have, for all HDP, it's going to fall somewhere in this circle, whatever the variables may be, it's going to fall in there somewhere. But I believe that it's going to vary within that location by manufacturer, manufacturer 1, 2, and 3 is what I chose as an example. These may be grossly exaggerated. I haven't done any studies on the material or any of that, but they have to vary based on variances in the material. They're not going to all be the same. They might overlap or they could be scattered even further apart, but each material is going to have its own sweet spot. And, being what I do on my off time is compete in high power rifle competitions. And so I see things in terms of a target and a bullseye. So Eddie's sweet spot seems like a bullseye to me, and then you have the rest of your target you're trying to hit, and then you're off the target altogether. And I think that really probably sums up your optimum welding zone, which would be Eddie's sweet spot. That's going to be your center of your target where you want to be. And then, somewhere you're going to meet the existing criteria. You're going to meet your peel, your shear strengths. But at some point, you're going to be off the target. But based on property formulations, based on your thickness, the production method, whether it's calendared or blown film, your texturing, all those things are going to make a difference. And I think as a result of that, you're going to have different sweet spots with your material and you're going to have different size targets you're trying to hit. And, we may need to look at reducing this so that you're not just meeting peel and shear, but that you're getting in there where it's not negatively impacting the geomembrane when you're welding. But I thought this was one way to illustrate a point. Um, and that point being that the variance is critical to understand. So if we have a trial weld, and these are assuming they're all on a linear plane here, your values are all the same. For material 1, you're in the center of the bullseye. Material 2, 3. Okay, this trial weld result put you all in the center of the sweet spot, your optimum welding zone. Well, what if that trial weld moves now? You may have, with material 1, you may still be in an acceptable passing. Maybe you're passing your trial weld, and maybe you're not damaging the geomembrane either. Material 2, it might be failing already at those values. And material 3, you still could be in the optimum welding zone, sweet spot. Similarly, you can move the trial weld results around, and you're still on target. You're still meeting your objective, at least getting a passing trial weld. Hopefully not damaging the geomembrane with material 1. Material 2, you're totally off. You're probably failing your trial weld at that point. And material 3, you're right on the edge now. And that'll become critical in the next webinar is if our trial seam is right on the edge and we don't know it's on the edge, you have an anomaly like we looked at in those graphs earlier in the presentation. How do you know that that anomaly doesn't put you out here somewhere? I mean, maybe it moves you closer to the sweet spot. Maybe it puts you out. That's something that we don't know, and that's why the manufacturers need to find a way and step up and uh, get this information available. Because at some point, there is a point of no return. There's going to be a point at which the heat permanently damages the molecular structure of the material. And I'm really focusing on that aspect here. There also is a minimum heat required to make your weld in the first place, and a minimum heat that may not yield long-term results at that too. There's a sweet spot on the low end of the spectrum too, but there's a lot of compromise on the heat and overheating it. On the low end, they're going to be more likely to fail peel and shear testing. So you don't see that too often. The installer tends to want to be on the high side. So we are seeing, what Kerry Rowe, Ian Peggs, and others talk about is, the damage to the molecular structure of the material, the OIT loss, and the potential stress cracking. Another reason why I believe that geomembrane manufacturers should provide the data is that HDP pipe manufacturers supply this type of data. From ISCO Piping, I took this chart out of there, but I took it out of their HDP Fusion manual just to illustrate, but they work with different equipment manufacturers, and they have 3 or 4 different equipment manufacturers and what the temperature, speed, and pressure should be. And as you can see here on, I forget which machine this one was, but they're all the same one for the next series of slides, but they provide a minimum temperature, an optimum, and a maximum. They give you guidance on how to verify it. For those of you unfamiliar with a pipe welding, you always want to look for uniform beads, and there's a minimum size. They recommend what size bead you should have, and then to get that bead, they have your time, your dwell time. So they provide the temperature, they provide the time, they provide the pressure, they have to join the two together. So how long it's got to stay together too. And then the cooling time is your weld cool time before you separate. And they have that information there as well. And I think, that's another consideration for geomembrane installers is that there should be potentially a weld cool down time. I don't know how much it applies to fusion welds. I know you wouldn't want to dump any water on them or anything right after you're done welding them, but I know people sometimes will air test them, as soon as the seam is done. And I don't know if there's any issue with that or not. I don't know if there's any studies on it. I haven't found any, but I know that extrusion welds, you'll see the installers will sometimes dump soapy water on it right after it's welded so they can start their vacuum test. And, that's artificially cooling down the weld substantially, and it's going to damage the weld and crystallize it and potentially lead to failure in the future. So there are variances in the welding machine configurations, and that's where I believe the geomembrane manufacturer should actually work with welding machine manufacturers. There's differences in wedge dimensions, wedge materials. You have porcelain, copper, stainless steel. Your contact area of the wedge with a geomembrane can vary sometimes depending on the machine and configuration. I have a schematic here that we took out of the US EPA document listed below that really shows you the hot wedge here. Direction of travel is from right to left. Your geomembrane's being fed in, and then it's in contact with the geomembrane. And then you have your rollers squeezing it together into a form sheet behind. So it's how long this geomembrane is in contact with the wedge that it's getting the heat. So there's some type of a coefficient of heat transfer there. And I'm no expert in any of that. I never studied heat transfer or anything like that, but I know it exists and it seems like it could vary. I know that, for instance, Leicester is advertising a new wedge. I believe it's a longer wedge, so the length would be longer. So they're stating that it can travel faster because they now have increased the surface area. So they're getting the same heat at a faster speed, the same amount of heat transfer. So I believe that's what's critical is that the geomembrane manufacturers figure out what that heat transfer coefficient should be. And I'm not the only one that believes this, talking to different manufacturers. Um, I was talking to them, and these are some of the quotes that were come back to me where they really feel like the manufacturer should be the one to decide the welding parameters. The first quote, these recipes are closely guarded secrets and not public knowledge. So why should the machine manufacturer decide the welding parameters for a particular geomembrane? Well, that's a good point. Same with the next one. Welding parameters and tolerances are dependent upon the geomembrane recipe and how it is formulated and produced. The membrane manufacturer should be providing guidelines about where the welding parameters should be. And then the last quote I have from the welding machine manufacturers, the machine manufacturers have no idea about the membrane formulation and what additives have been incorporated into the membranes, which is critical. That's a great point. These are all great points, How can the welding machine manufacturers set the guidelines for the material when the material may vary? And, what is the liability in doing that? That's where it kind of gets into a gray area of warranties here. Who is responsible? Who's going to be responsible for the heat impacted zone and any stress cracking that occurs as a result of the geomembrane overheating? Is it going to be the material manufacturer? Is it going to be the installer? As soon as the installer um, does anything to start assembling that seam, excuse me, um, to weld that seam together or join it, the material manufacturer is going to say that's on the installer. Well, a lot of the installers are getting their information from the welding machine manufacturer. In preparing for this webinar, we talked to several installers, and we asked them, where do you get your settings to use? And they said the manufacturers don't have them, so we got them from the welding machine manufacturer. Well, to me, maybe the welding machine manufacturer's taking on more liability than they want to, but that's just my personal opinion. But it goes further. The CQA personnel, are they going to be blamed? They could be blamed as well. The certifying engineer, why didn't they catch it? And then the site owner. But ultimately, the site owner is the one who's responsible. The site owner is the one who's going to be sued by the EPA or regulator, whatever regulatory agency. The site owner is going to be the one getting all the negative publicity, and the site owner is going to have to deal with it and pay for remediation and anything that goes wrong. And then they're left to try and sue anybody else and get money back and retribution back from anybody else. Um, well, not only their operations may be impacted, but remediating it and doing future remediation as well as a negative image. And then the engineer's construction certification, as I mentioned earlier, the engineers, they follow the CQA plan for certification. They follow technical specifications, the construction drawings, and they sign off that the project wasn't constructed in accordance with these documents. So they go through their checklist and they review and make sure the material met the project's requirements, subgrade, ambient temperatures, if there's anything that was outside um, what was stated in these documents, and they'll write up what procedures were used to correct them. It might have been where they shaded the welding apparatus or shaded the seam so they got it down into the correct temperature, things like that. So everything's going to be checked by the engineer before they sign off on it. And anything to do with the seam and the adjoining membrane being damaged, there's nothing they can do about it if it's not in the specifications. Now, one of the things the manufacturers always argue is that your site's going to have its own variability. It's going to have different moisture, humidity, you know, dust, dirt, things that they can't control, which that's a good argument, but there still has to be a baseline somewhere. There has to be some type of baseline that can be adjusted with different variables. And this is just a video I'll play for you that I was illustrating, things will vary. Here's the weather. We have some installers out there. They got a good downpour and they got a hard hat on the fusion welder to at least keep it dry while they're welding in the downpour. But quality is even secondary at this point. This is a big safety issue, having electrical components, electrical cords running all over a conductive geomembrane, which it's just an HDP geomembrane without the conductive backing is conductive, and they're welding in a downpour, but something that shouldn't be done, now that's something that's beyond the installer or the manufacturer's control, but there are actually installation guidance documents from the manufacturer that don't address weather. So that aside, I wanted to look at what can be done now, since we talked about, that it is a problem. Overheating is a problem. What can we do now because the manufacturer's data is not out there and readily available? One of the biggest things is reducing heat during both fusion and extrusion welding. So you obtain necking during the peel test, necking or elongation. You can see here the coupon is not breaking at the edge of the weld, it's stretching. And the stretching is a better indicator. It may not be the best indicator yet. There probably is better indicators, but at least it's an indicator that the geomembrane still is flexible enough to elongate rather than just break. Another example of elongation. Here's another coupon, again, showing here's the seam. It's a peel test. Geomembrane is elongating on both the upper and lower sheets there. It's not breaking right at the edge of the weld. But what's common in the United States, and again, there's nothing saying to the contrary that this is bad, is that we're seeing where most of our peel and shear test, well, most of our peel tests, the shears usually elongate unless there is an issue, but the peels are breaking right at the edge of the weld. And it's my belief and the belief of others in this industry that if we cool down the heating a bit, you can return back to the the necking that you're seeing on this previous slide without compromising the integrity of the weld and without compromising the integrity of the adjoining geomembrane. Excuse me. There are some installers, actually, I know, since I've been talking at conferences, and they have taken it upon themselves to cut back on their heat a bit. And I haven't talked to them recently, but I know they were doing that. Excuse me. And so I believe that's a great first step, and I think more people should be taking this approach and trying to be proactive and, be less worried about the peel and shear, but pay attention during trial seams. We don't want to have a high failure rate on the peel and shear, so there's got to be a balance. We don't want our destructs all failing again, but there has to be a balance. We can monitor the squeeze out of the fusion welds in the field during trial seams and see what you see. Again, same figure from before. You have your weld, dual track weld here on each side, and then your squeeze out. And you can see that there's a pretty wide air channel here, pretty uniform squeeze out. Usually you're looking for a uniform squeeze out. You don't want to see a lot of thickness reduction in the weld. But you're looking for uniform squeeze out on each side of a single weld, and then usually they're going to be pretty similar on each track of a dual track as well. And that's, one way to start, but if there's no guidance saying that we can reject anything, then you have seams like this where the air channel is greatly reduced. There is a thickness reduction, and there's nothing you can do about it, which currently is the case here in the United States. And here's another example where, this was significant overheating. We just had the coupon cut out from really between the weld or the edge of the weld, but you can see this air channel was greatly reduced to only 1.25 millimeters. And not only is that compromise in the geomembrane, it was a 60 mil product, 60 mil, 1.5 millimeter product, but it caused a fiasco for the installer. I mean, they lost several hours worth of work, and most of their crew lost work because this was one of the last things remaining to be done on that particular day. So they lost a lot of money and efficiency on this. So, I think the installers are struggling as well because of this. And if they had better guidance from the manufacturer, you wouldn't have welds like this. And, if you get the optimum conditions, it won't be slowing them down and they'll be doing a good job. Looking for signs of time and speed issues. This is a burnout, so obviously there was a speed issue. Maybe the wedge got caught up on something, but you start seeing wheel spins too, which I don't have a slide of. But the tracks will be bunched up but not burned through. There's an issue there, and those will show up typically on a data recorder, so you'll have them there as well. But without data recorders, you want to be looking, and even with data recorders, you need to be walking the geomembrane seams. Extrusion welds, monitoring the squeeze out on each side, trying to see that it, for the most part, should be pretty uniform. If it's not uniform, sometimes there's more pressure on one side than another, or there could be something with the tip. Maybe they did something to the tip, modified the tip, or the tip's broken. Monitoring the extrusion weld thickness during trial welds. You're going to have your extrudate, and the thickness of the extrudate really should be equal to the thickness of the geomembrane. So it should only be above the geomembrane, the same thickness. So if it was a 1.5 millimeter thick geomembrane, the extrudate should be 1.5 millimeters at most. And you'll see that in cold weather or cooler conditions. A lot of times you get installers and they're lumping it up. They're making a high weld. And there's, different studies that seem to be showing that that's not a good idea. That's resulting in the weld cooling at different rates and resulting in crystallization of the weld and a weak weld ultimately. Looking at the backside of extrusion welds for heat penetration, especially your trial welds, but if they cut out any patches, if you're doing destructs, look at the look at the back of the sample for the heat penetration, this is overly penetrated here. You can see where the geomembrane's bunching up on itself. I had a slide I thought in here of a good one, but when I went through the deck before the meeting, I don't see it. But it should just be a nice uniform penetration, barely penetrating. It shouldn't be degrading the back of the geomembrane very much. Another example here of the heat penetration, and this one burned completely through, and this one was at a T, and that's where it's common where you have burn through an extrusion weld is the T bead because they're overheating that T area several times in the formation of the T. This one is another burn through at a T. And you can see the T weld here. They have to come different directions. They're going their one direction to put the weld down, then they come back and either make one pass, or in some cases, they'll make multiple passes to complete the T. So this area in here is being reheated several times, and then it's already been heated up by the fusion weld, and they trim the lap off to make these T beads, so you're putting it right on top. So you're already reheating that area there, and it's a common area for burn through. So one of the practices that we've implemented as a CQA firm is we like to have the installer, when they're doing their trial welds, weld a T to that trial weld or on the scrap so that we can examine it and we can look for it, see if there is any burn through. It's a simple, easy practice. It doesn't add any extra time. They don't have to cut a coupon out of it or anything, but they can do that. Then minimizing the number of overlaps to repairs and extrusion welds. Again, every time you're heating an area, you're increasing that risk of changing the chemical composition. And I think I'm about a half dozen slides or so from the end, so I want to remind you here too, use your question and answer feature to write down some questions here at the end, and I'll try and address them. That'll be coming up here shortly. But yeah, so I wanted to show you, overlap, and this could have all been cut out and one patch put in here, and it would be a lot less heat, and reduce the chance of all the overheating of the geomembrane. Things like that should be avoided. You see this quite often too, where there's an extrusion bead on an extrusion bead. That should never happen like that, at least with something that small. They should cut that out and repair it with a larger repair. This one here, same thing. It was a fusion weld. They did some topping here. It looks like for the T, they just ran it longer, removed the flap, but then they put another bead on it as well. So that can be cut out and patched and reduce the heat, get the heat away from the extrusion seam, except where it has to cross for the repair. Avoiding welding of the fusion overlap flap. That's used to be a common repair procedure, but we recommend against it because you have your fusion weld here. It could be a solid or dual track, but either way, you're going to have an outside edge there, and then your flap extends beyond the weld a little bit, usually a few inches. The procedure is to heat tack and grind that down and then put an extrusion weld out there. Well, that extrusion weld now is bordering on that heat affected zone from the fusion weld. So you're getting heat going back into that same area. And then avoid topping, which is topping. They remove the flap altogether. They grind the edge of the extrusion weld, such as for a T-bead. I mean, you have to do it for the T-bead, but other instances should be avoided. And then they apply the extrusion bead. Well, now you're reheating not only the extrusion weld, but that heat affected zone. So you're adding more heat each time you do that. So again, it's a recommendation in the industry to avoid that. Using the same welding rod. So this is a specification you'll often see in the technical specs or the CQA plan, is that the welding rod must be of the same composition as the parent material, the geomembrane. Well, what does that mean? I've asked multiple people what that means. People in the industry, that are well known, and nobody will give you the solid answer on it. People will say, well, it just has to be HDP if it's HDP geomembrane or LLDP. But I think the graphics I showed you earlier illustrate differently. I think that my belief is it should be if you're using GSE material, the Solmax GSE brand material, you should be using that same welding rod that came from that batch that was used to make that material, at least the same manufacturer, because um, their proprietary formulations may be different. That if you're using Agru, if this was HD rod, maybe it's not, doesn't have the same melting point as the GSE, and that can be problematic if it doesn't. It's going to cause issues with quality welds and long-term performance, which may be unknown. Um, so I believe that answered, that question, just doing this study here and what we're doing in the webinar so far. So really, that's the bulk of my presentation for um, this first webinar, the missing link, welding data supplied by the manufacturer for your heat, speed, and pressure. Up next, I'm going to do in December, wedge welding data recorders, the unspoken truth, because I believe there are things that we need to look at about the data recorders. I believe they're a good technology. I just think that there's a lot of things that aren't understood about them that need to be understood for them to be used properly. And again, until we get the information from the manufacturers on what's the proper heat, speed, and texture to use on, or heat, speed, and pressure to use on their material, we're really kind of shooting in the dark on interpreting their data. But the data recorders may ultimately play a role in gathering the data that helps the manufacturers narrow it down and provide that window as well. That webinar is going to be Thursday, December 19th, 2024 at 12:30 p.m. Eastern. We're going to try and get on the normal schedule of every third Thursday of the month having a PDH hour with Glenn. And I look to see you, looking forward to seeing you then. I'm going to open it up to questions and answers if you have any. I'll see if there's any available here in the Q&A button here. All right, I see a few questions. I'll see what I can. Okay. Um, okay, someone asked, Tess asked, is there a recommended lifespan for the welding equipment? Or am I aware of the most common reasons welding equipment fail to work properly, i.e. electrical wear and tear? I don't have any, I've never seen any requirements on the lifespan. They're fixed on the fly a lot by installers, which I tend to raise questions in that regard too. What is their experience? Are they properly repairing them? Um, I think the manufacturer of the machines should be involved in those decisions sometimes where I think maybe they're not. Every one of them will come in with a calibration that says, they're calibrated. You need to recalibrate them per the manufacturer's instructions and frequencies. But how often is that done? There's never really a requirement as a CQA person where I ever see where we got to make sure that they're calibrated. And then they get banged around, they get dropped. It's a real gray area, but it's a great point. What is the lifespan? I'd like some manufacturers, and I'll try and address that. That's a great question. Um, Another question from Tess, actually, is there a rule of thumb on how often, frequency of when the heat on the machine should be reduced outside of doing trial seems more frequently, i.e. the temperature increased X degrees since trial weld, so we need to reduce the heat of the welding equipment by X degrees? No, there's no guidance that I've ever found on that. That's another thing that I think the manufacturers have to work on. I think the manufacturers can provide that and work with um, machine manufacturers on it. We can all work together on these jobs to get that answer, but right now there is nothing out there. A question from Paul. How often do you see stress cracking? That one I am not aware of. I need to find that out and I'll try and address that. I know that there has been stress cracking. I know several years ago I talked to Dr. Ian Peggs, and he was asking me if I had seen any because he was being told that there was no stress cracking and that it was an outdated issue. But he then stated that he firmly believes that it is an ongoing issue. It's just not occurring. And I think part of this presentation is showing why we may not be seeing it right now, but that we might be seeing it again in the future, unfortunately. Derek sent a question in and asked, do I feel if there are inadequacies in GRI, GM9 for cold weather seaming? I don't remember it off the top of my head. I do think that there are some things. I know we did discuss it as a panel. There was a panel group at a conference I was at, and I don't know what happened to that document, but Dr. George Kerner was there taking notes. There was a panel, Eric Blond and Eddie Weiser, Dave, and some others were on. Dave McClowery from formerly from Demtech. I don't know that offhand, but one thing I will say about GRI, GM9 is that it really needs to be planned for ahead of time. Quite often, my project managers are telling me that we go into pre-con meetings, September, October here in the north, and the cold weather is gonna probably hit before the project's over, and they try to deal with it at the pre-con meeting and no one wants to hear it. But there's a bunch of requirements for engineers in GRI GM9 that need to be addressed, and those should all be ironed out before the project gets to the cold weather point, or it's going to cause delays. And as for the inadequacies, I'll try and look at that and I'll try and find out where the document stands. And then Tess had one last question here I'll try and answer. I know it's 1:30. I'll try and answer this in a minute or so. Tess said, so we know that the heating the geomembrane over and over weakens the geomembrane welds. Have we looked at how the constant heat of the waste after it is placed affects welds over time? Or does waste not get hot enough to have this be a concern? I know there's studies on this test with Dr. Kerry Rowe and some of his colleagues have some studies on this. I don't know the exact answer to that question. I know that they are looking at the heat affected zone in particular. They also were doing some samples in brine solutions and such. I know that their recommendation from one of Dr. Rowe's lectures earlier this year is that the geomembrane should always be tested in the leachate it's going to be in contact with, or whatever chemicals it's going to be in contact with under those same conditions, so the same temperature. It should be replicated as best as possible. But I don't particularly know about the seam. I know the heat affected area tends to degrade quicker. So that, and I appreciate all your questions and it being interactive. I will try and get back to those of you who have questions that I didn't thoroughly answer. I'll see if I can find answers on that. And I appreciate you all tuning in. And I look forward to seeing you all in December. Thank you for participating in this first PDH hour with Glenn, and I'll see you in December. Thank you very much.